No, I think I know what I can do. It's fine. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for all the students that are here. And we just pray you be with us today, Lord. In your name I pray. Amen. So, yes, 2979.
It says it's incorrect. Oh, wait, that's fine. I heard 2929.
2584.
Wait, is yours up? Nope, it just like, oh, no, there it is. 2585.
84. 84.
Are you trying to guess this up?
20,
I'm trying.
2584. That's right. 2607.
No one tell Leanne, and then just tell Paige wants to begin this video.
I'll make some like 50-point bonus for the course if your attendance gets over a certain percentage. 42. 45. I'll strategically calculate it so he can't overcome. Like I gotta look ahead, like discover like what your current percentage is and work out some equations, you know. But I'll make it so he gets close, but he can't quite get there. 52, 37. There you go. I think that's enough spite for one day.
Wait, but we did 5 last time. We need to do one more than last time.
Oh, you do make a convincing case. This should.
You can't end on an even number. 29 should be a prime number. 7. Prime number. I like it.
All right, let me close this miserable thing. It'll slow me down a little bit, but I do have a PDF of it I can look at. I have not synced Blackboard with.
Yeah, you can see it on here.
I haven't synced Blackboard with Top Hat yet, so your current Top Hat percentage is not in the Blackboard.
I missed pre-attendance. And then
That's not pre-attendance. That is pronounced pretendance.
pretendance. Yeah, I missed when I was in.
I'm very proud of pretendance.
Well, and you got attendance like the day you missed, right?
Pretendance was one of my more ridiculous features this semester. I'm very proud of the pretendance.
Oh, my plan is yeah, I missed. That's.
All right. Sorry, I am going pathetically slow today for some reason. So I'll make up for my sad pace by being vague and getting through it more quickly. No, I'll try to draw a picture. So the three things we want to talk about, classical straight edge and compass constructions here for just a few minutes, and I'll try to at least describe what's going on best as I can. So the basic claim is that one, doubling the cube, 2, trisecting an angle, and 3, squaring the circle are not possible. How? Did I start recording?
Yeah, it was before Top Hat started.
Oh, okay. You worried me for a second there. And so, well, here's the question he asks. Is it possible, using only straight edge and compass, to construct a square whose area is precisely the area of a given circle? So, if you've got a circle like this, can you construct a square that has the same area as that circle? My picture's not quite right, but you get the idea. The question is, what is this, constructing, classical construction with compass and so forth? So he starts out, he says, let 1 denote a fixed unit distance. Then any distance is determined by its length a, which allows us to view geometric distances as elements of real numbers. So, to start with, you've got some sort of basic length that you call 1, and that's a building block for compass and straight edge constructions. And he says, using the unit distance 1 to define a scale on axis, we can then construct the usual Cartesian plane in R2 and view all of our constructions as happening in the plane. A point, xy in R2, is then constructible, starting with distance 1, if and only if its coordinates x and y are constructible elements of R. So you can talk about, the plane. You got some point out here, x and y. This is constructible if and only if x and y are constructible. A stupid example would be 1, 1. 1, 1 is constructible because we assume 1 exists, right? Like, that's our basic building block, is the number 1. There's some kind of unit distance. We can build things from that. He says, the problems above then amount to determine whether particular lengths in the real numbers can be obtained by compass and straight edge constructions from a fixed unit distance. He says the collection of all such real numbers together with their negatives will be called constructible elements of R. All right? And we're just going to identify a number with the length which it represents, okay? So the number 1 and the length of that line segment will be identified, all right? Fine. And so here's what he says. He says, each straight edge and compass construction consists of a series of operations of the following 4 types. So here's the following 4 types. So number 1, you can do what? The first thing you do with a straight edge is you can connect 2 given points with a straight line. Not to be confused with a straighter line. 2, you can find points of intersection of 2 straight lines. This is another allowed geometric thing. You can find points of intersection for pair of lines. Possibly. Of course, you don't have to have 2 lines intersecting, right? You could have parallel lines; those would not intersect, right? But if they do intersect, you can find that point. All right. 3, you can draw a circle with a given radius and center. So here, this radius, I'm assuming, would have to be a constructible radius, right? And the center would have to be a constructible point, to connect with what we've been doing. And then step number 4, you can find points of intersection of a straight line and a circle, or intersection of 2 circles. So you can also find, 4 is, you can find circles intersecting with stuff. Find where circles intersect with each other or lines. So, this is classical straight edge compass geometry. So do you guys know, have you all had high school geometry? So you know if I had, for example, you give me 2 points, right? We can connect them with a straight line. And then how would I find the midpoint of that line? Using add points and divide by 2. Spoken as a true disciple of Descartes. Descartes. We've been doing analytic geometry since Descartes. Why aren't we still doing it? Yeah, I know. But divorce yourself from your understanding of analytic geometry. You must use only compasses and straight edges. How do you find the midpoint?
Draw a circle
Draw a circle from where?
with the, like, draw a circle
Mhm.
where the edges touch both points. Oh, I mean, that works too.
Yeah,
That one too. Do it with the other
and then do the other one.
Oh, no.
No, that, yeah.
No, I was going to say just draw a circle.
And then see where they intersect, and draw a line down, and that intersects the midpoint.
I took rather ridiculous circles to do this. You don't have to use those circles to do it, but when we do that, so that was 3. So I started with 1, we connected the points. I did 3, I drew a circle with a given radius and center. And then I can find the points of intersection of the circle, right? Like this one and that one. And then, of course, I'm allowed to connect these 2 points with a line, like so, yeah? And if I did that right, the intersection point of that line with the original line segment will be the midpoint. So there's a way to define the midpoint without an ounce of analytic geometry, right? Just pure classical compass straight edge construction. I've now taught you all of Math 307. Just kidding. I'm just kidding. This is me hard unselling Stephanie on Stephanie, listen to me. Bethany, you've become Stephanie today. That's good. What kind of transformation is that? What does it take to transform a Bethany to a Stephanie? Like what kind of? Is that like a Legendre transformation? Is it what is it? What kind of transformation is that? You don't know? I think that's a me foolishly teaching 2 classes back-to-back transformation. All right, anyway. So the point is, there are numbers which are constructible, right? If you give them, if you start with numbers, you can do this. And so what he claims in here is, he says, it's an elementary fact from geometry. If 2 lengths A and B are given, then one may construct using a straight edge and compass lengths. So here's the theorem that I won't really prove. Given lengths A and B, in other words, numbers with lengths A and B, you can construct, well, A plus B, A minus B, and you can also do what? You can also construct AB and A over B. How do you do that? That actually has very little to do with this course, like the specific mechanics of how that happens. But just since we're here and since I don't want to say too much in Liam's absence, let me draw a picture. Don't worry, that'll wear off soon. My not covering material when he's not here. So, what's that? There's a video? Oh.
Watch the video between when this ends and when the next one begins.
What? Yeah, borrow the same for once on that.
Watch it at 3 times speed. Get all caught up.
All right, I'm trying here, guys. I don't know if I can recreate this picture very good or not. In this triangle, this distance is 1, and then he says this distance here is B, the distance from here to here is A. And allegedly, if you set this up, this here, actually, I don't think this is the sort of you do it. Math 307 is actually not about this. It's about rather different things. But the tools are the same, right?
That's number 3. Apparently,
307, curses, I meant to say 305.
okay.
I can't even get my insults correct today.
It's CPAC. It's the CPAC. The essence of CPAC is messing us up.
We are still recording.
Thank you. So somehow, if you start with A and start with B, you can use those to somehow, together with the 1, construct this triangle. And in so doing, the length of that is AB. I don't know. There's probably a YouTube video that you could find where this is actually shown. I don't actually personally know how to do that, I'll be honest. All right? So, I mean, but somehow, through a series of 1, 2, 3, 4, we can construct AB. And he has a picture which I will not, I mean, I can draw the picture, but I'm also really not going to add anything to it. I'll put it up here, though, just for the sake of completeness. So his other triangle, he puts 1 down here again, and up here, somehow he has A over B. The net distance from here to there is A, allegedly. And this down here is B. Now, I honestly, guys, I don't know quite how you get from A and B to how you actually define this length here to construct A over B, but there apparently is a finite sequence of 1, 2, 3, and 4. All right. I mean, he has a couple sentences here that he says, the first 2 are clear, and the latter 2 are given by the construction of parallel lines. See the figure. Okay. So, I mean, in other words, this line is parallel to that line. And where are the parallel lines in here? Oh, I forgot. I didn't finish the picture. There's a parallel line here. He said by the construction of parallel lines. Oh, that's another thing you learn in geometry, right? How to construct parallel lines. I'm not sure I remember how to construct parallel lines right off the top of my head. Like, I remember this from high school geometry, the parallel, because I just thought it was so cool, this perpendicular bisector trick. I mean, that's just neat. We use that in drafting, too, to find perpendiculars. It's a nice thing. Back when we used to do drafting with, like, pencils and papers and stuff. That's actually what is the origin of my neat handwriting. Before I took drafting, my handwriting was very bad. And I took drafting. I learned to put in things block caps. And ever since, my handwriting has been, better. My wife still says it's bad, but anyway. We can't all be perfectionists. All right, so any questions about this? All right, so long story short, we can construct these numbers, and furthermore, he says if you, and this is another bit of magic to me. Maybe you guys can see it, but if this, I mean, I can always cheat with analytic geometry and understand why things are true. That's true. But if this distance is A, and this distance is 1, all right, so if I construct a circle which has A plus 1 as its diameter, all right, and then I look at the perpendicular bisector to that, like this, then that will have square root of A.
Is that line the center, or is that?
It's not off the center. My picture has it too close to, I mean, the picture he has in figure 2, it's more to the side. It's definitely not a radius. And I think that I probably could work out, right? I mean, I mean, I could see if, okay, so there's two separate questions. Like, do you believe that you could construct that with a compass and straight edge? All right? You do? Okay, good. Then the question is, why is that the square root of a? I mean, I think we can all agree we can construct the perpendicular bisector. Why is the length of that square root of a? Draw the right triangle. Which one? See, but oh, this one over here.
Yeah, because this will probably be the 1, 1, 2. Well, then isn't that a?
I feel like the radius of the circle should be the square root of a plus 1, right? Well, excuse me, a plus 1 over 2, right? Oh yeah, why square root? Good question. Does that even help me though? I mean,
I think that is helpful. But I mean, if you have the radius is a plus 1 over 2,
uh-huh.
that gets you to a plus 1 over 2 on like that horizontal line, but that's also from the horizontal line back up to the circle. So now you have the 2.
Wait. It's also where?
So like on the horizontal line, right in the middle,
Uh-huh.
you're at, from that middle point.
So draw a middle point on the circle.
Yeah.
So like right there would be,
Yes.
yeah.
And so you know that the length from that middle point, so like over to the left to the edge of the circle is a plus 1 over 2, but also from that point straight up to the circle is a plus 1
Uh-huh.
over 2.
Okay.
So now all you have to do is make that triangle. You have 2 lengths and solve for the hypotenuse.
Make that try.
So connect the point.
Do I need to blow my circle up a little bit? Is it all happening up here? What you're talking about?
Yeah. So
Here, you drive.
you know that this
Uh-huh.
is a plus 1 over 2, but so is this.
Right.
So now all you have to do is find that using the Pythagorean theorem.
Oh, okay.
But then what is that?
That is,
Oh, but that might not.
phooey.
Yeah, because that's off.
Still not the one we want.
That was my thought.
It seems so hopeful. Fun fact that red,
Wait, if you know the 1 and the square root of a, you could use like the arc sign or the.
okay, what we got here?
Cosine.
Let me erase all the,
Sorry, tangent. Opposite over tangent.
so what I'm trying to do is to show that whatever the length of the purple line is, it makes sense to identify it as being the square root of a.
Okay, so we don't know it is that. Okay.
Yes, yeah.
Because I was thinking for a second, I was like, wait, we have 2 sides to right triangle. But then I was like, wait, what are the other 2 for?
Well, yeah, I mean, if we, admittedly, if we could find the length of, like this over here, or this over here, we'd be in business. But we can't,
Isn't that a right triangle right there?
I do think that's a right triangle,
So then
yeah.
you have.
Yep. And we know that the hypotenuse's length is a plus 1.
Yeah.
Oh, wait. Are you trying to say, because then you have like 3 right triangles, right? You have the one to the left, the one to the right, and then the big one.
Yeah.
So somehow can you solve like 3 equations?
Oh, maybe similar triangles? That's not a bad idea because we can see that geometrically this angle and that angle, right? So that would say square root of a over a is equal to, like, looking at this one, the opposite over the adjacent would be the opposite, which here is 1, right, over the adjacent. Yeah, that actually says that the square root of a, whatever that thing is, squared is equal to a. We don't, I mean, if I don't call it square root of a, if I call it Pac-Man, we've just proved that Pac-Man squared is a, which means that Pac-Man is a good candidate for square root of a. Yeah. Yes, yay, similar triangles for the win. So there you go. The larger point here is that we can construct a square root of a constructible number. Again, using straight edge, so forth. So what's the deal? And he says, okay, well, what do you got? He says the collection of all constructible elements is a subfield of R. So the collection of all constructible numbers is a subfield of the reals. And all right. And then okay, then what he does is rather technical, all right? What he does is he examines, from the perspective of analytic geometry, actually, what do possible, like if you give me, if you have points, if you have constructible points already, right, and those are related as intersection points to something on a circle, intersection of a pair of lines or a pair of circles, like what is the algebraic relation between the given constructible point and the new point that you're forming by intersection? Like, what is the possible algebraic relations? And by studying the equations which define, like 4, right, he's able to prove that they're, again, just square roots or linear combinations of the constructible numbers that are already there. So like that's it. I mean, that's all that you can have is like a square root or a linear combination in the sense that I've shown you of what you already have. What that means then is that if you have a finite set of constructible numbers, it's going to be formed as a well, let's see here. What does this get you if you start with? I mean, A could be. I think it gets you rational numbers, right? Am I wrong? I mean, I can construct 2, 3, 4, 5, right? -2, -3, -4, -5. I've got products of those, of course. I've got like 2 over 5. Those are all constructibles, right? So like, anyway, I'm not getting to the point fast enough here, so sorry. The larger point here is simply, let me get to it. This is the proposition, which if I had my notes, I would have written down 20 minutes ago and would have spared you all these details. Proposition 23. An element alpha in R is obtained from a field F, subset of R, by a series of compass and straight edge constructions. Then F alpha over F is equal to 2 to the K. So, here alpha is constructible from elements of F, meaning you start with some subfield of the reals, all right, and then take that and do compass straight edge constructions on it, then you have an extension of degree 2 to some power. Okay? So, and then the theorem 24, yep.
So, but you said like you could construct square root of a number. So like, if you had f join square root of 3 over something, didn't we see that something like that was like degree 3?
Square root of 3 is degree 2.
Something, it wasn't square. Oh,
The cube root of 2 is not constructible unless you've already got the basic building block to get it. So, like, what did we see? Didn't we see now I'm thinking of the sixth root. The sixth root is degree what? Degree 6. Yeah. Let's look at the sixth root of 2, for example. Sixth root of 2. Is this constructible? That depends on what you got to work with. What's your basic building block? This is actually a very good question because it exposes what this proposition means. So the sixth root of 2 may or may not be constructible depending on what you're starting with. If you're starting with, if you have f equal to, say, q adjoin, I don't know, third root of 2, then I think the sixth root of 2 is constructible because what's the degree of the sixth root of 2 with respect to the q adjoin cube root of 2? What's the minimal polynomial for the sixth root of 2 using q adjoin the cube root of 2 as your base field? I heard x squared minus the cube root of 2. If we plug in the sixth root of 2, does that works? Yeah. I think we talked about this last class. So that means that this is 2, which means if you had in your starting point f the cube root of 2, you could construct the sixth root of 2. However, if your starting point if your starting point was rational numbers, then you'd be out of luck. Because then the degree of, well, more to the point, if we look at the extension by the sixth root of 2 over the rationals, that has degree, what? 6, right? Which is not equal to 2 to some power k. So the starting point matters. The question is, what data do you have to work with? You start with that data, you feed it to classical compass straight edge constructions, and that gives you a set of numbers that are constructible. Right? Sort of like, you get a Lego set, you have a certain collection of blocks, you can build certain sets, right? And so F is like the set of Legos that you got to work with, but we should talk about more things in terms of Legos. We don't spend enough time talking about Legos. I should bring Legos. I would teach operations research here if the department would agree to buy me a Super Star Destroyer. Like the whole class would just be about like constructing a Super Star Destroyer in 10 minutes as a class. Yeah, but I get to keep it. That's the rule. And every year we build a new thing. Yeah. I don't think I actually do, but okay, so getting to the point, doubling the cube. Thinking about that. So what do I mean doubling the cube? So here, side x, right? X, given. You want to construct a new, bigger, better cube with the volume equals to twice x cubed. that would be doubling the cube. Can you take, a given cube with length, side length x, 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 and can you come up with a new cube with, length with height y, y, y? Well, that would mean you're getting 2x cubed equal to y cubed, right? So how would that relate? What would that say? I would say y is equal to what? The cube root of 2x cubed, right? Or, well, the cube root of 2 times x, yeah? If you could do that, that would imply that the cube root of 2 was constructible. Because if x and y are constructible, if x is given and y can be constructed, then in the the field extension formed by adjoining y to the initial field containing x, you have the division of x over y, right? You can divide those and you get the cube root of 2 is in your extension. But this we can't do because the cube root of 2 is a what? It's a degree 3, yeah. It's not a degree 2 extension. I suppose if you played games with the particular lengths of the given cube, maybe you could double the volume constructively, right? But you'd have to conspire to make the initial set of constructible numbers you're working with just happen to not need a degree 3 extension to get the new length. It seems like it's possible, but it's not generally possible for any x, and that's the problem. Any cube. Can you double the volume by straight edge compass constructions? All right. Now, I have 1 minute. So the other one, the trisecting an angle, let me run that down for you. So he says it's certainly possible for some angles, all right? But he gives a specific argument for why you can't trisect 60 degrees. Because if we can prove that you can't trisect 60 degrees using straight edge compass constructions, then they all fall down, right? So suppose, look at theta equals 60 degrees, try to trisect that angle. So that would mean that, well, by the way, cosine of theta, everybody knows it. All the kids know it. Cosine of theta is 4 times cosine cubed theta over 3. You guys remember this from trigonometry, right? 4 times cosine cubed theta over 3 minus 3 times the cosine of a third of theta. Yeah. Now, so if you put 60 degrees into that, and he says, okay, so set beta equal to 20 degrees, right? So theta over 3 equals to beta, right? And then what does this equation look like? Cosine of 60 is a half, right? 4, what's that? Cosine, oh, wait a minute. Oh, I'm doing the wrong thing. I don't want to set beta equal to 20 degrees. I want to set beta equal to the cosine of 20 degrees. I'm an idiot. Okay, so then 60 over... So then the cosine of theta over 3 is equal to what? Beta in that setup, yeah? So what you're looking at is 1/2 is equal to 4 beta cubed minus 3 beta. Which he rewrites as 4 beta cubed. Oh, so he brings the half to the other side. All right. Brings the half to the other side. And he rewrites it as 2 beta cubed. I'm actually almost done here, guys. Minus 3 beta. Oh, come on. Minus 3 times 2 beta. Minus 1. And then he says, let alpha equal to 2 beta, and then you've got alpha cubed minus 3 alpha minus 1 equal to 0. But Q adjoin alpha over Q has degree 3. That's that example I told you we come back to. So yeah, can't trisect an angle. Because if you could, it would amount to making a degree 3 extension of constructible numbers, which we can't do.
So we just can't trisect 60, or we can't do
We can't trisect certain angles.
certain.
Right. Now he actually does, because this is Dummett and Foote, and Dummett and Foote is a beast. He explains that, let's see here, he says which angles are constructible? Angles 1 and 2 degrees are not constructible, but the he says he's able to work out that 3 degrees, in particular cosine 3 degrees, sine 3 degrees are constructible, and from that you can any multiple of 3 degrees you can construct. And I suppose that means you can deconstruct it as well. Trisect it, yeah. Anyway, that's just a kind of, rather, I mean, to me, deep and perhaps surprising application of field theory to geometry, right? I don't think, I don't know, like every so often somebody discovers something new in this. It's not my bag, but, like one of the things Gauss is really famous for is constructing this, what was it, 19 or I forget, it was either 19 or 17-sided polygon. It was thought that, because you've heard of the Platonic solids, right? So like playing these sorts of classical geometric games, like most of the things have been found since the time of Euclid, but every so often, a very, very clever person comes and finds something new here, hidden in the wherever. But anyway, next up, splitting fields. So I think I'm allowed to go get coffee now, right? All right.